working? Yes. Okay, so thank you for the introduction. My name is Anastasia Shuba. Closer, okay. My name is Anastasia Shuba, and I'll be presenting NoMoAds to you, which is a system for effective and efficient cross-app mobile ad blocking. And this is joint work with my advisor, Athena Morkapoulou, and Zubair Shafik from University of Iowa. So I'm sure this has happened to all of us, where we're trying to browse some news, or we're trying to play a game and an ad pops up and distracts us from what we're trying to do. Aside from being intrusive, ads also cause you a lot of overhead in terms of network and CPU usage. And on top of that, a lot of ad libraries collect your personally identifiable information, or PII, for tracking and personalization purposes. Finally, some ads have even been shown to spread malware. A little bit more background on ads. The way they work: when you have an app that wants to request an ad, it could be a browser app or it could be a game. It will send an HTTP or HTTPS request to the ad network, and then the ad network will respond with an ad that will pop up on your screen. Now, on desktops, ad blocking has been largely explored. I'm sure everybody here has heard of AdBlock Plus, Brave, and uBlock Origin. And the way these ad blockers work is they block URLs within those requests based on some rules that follow a very specific syntax. So here's an example of one such syntax from EasyList. And if you want to create an ad blocking list, you create multiple rules for multiple pages where you want to block ads following this specific syntax. You repeat the procedure for multiple pages, and you end up with some 64,000 rules that are on EasyList. So as you can imagine, this is a very tedious process. You have to make sure that your rule follows the syntax, blocks the ad, but does not break the web page. And if the ecosystem changes, you have to update your rules, make sure they're not redundant, and so on. On the mobile devices side, things are even less explored. So in this slide, I will review the most closely related work. There's more details in the paper about them. So there are some apps, such as DNS66 and Disconnect, that also block ads based on a list. So they're not automated. They just follow a list. And they're actually less fine-grained than EasyList, because EasyList blocks based on URLs. And these lists typically block based on hosts and domain names. And this can actually be a little bit problematic, because some domains are multi-purposed, so they might serve ads, but they might also be serving content that is essential for the functionality of the app. And if you block that content, it might break the application. The nice thing about these works, though, is that their lists are often more mobile specific, so the list of hosts and domain names were curated for the mobile device. And because they use a VPN-based solution where they intercept traffic, these apps can block ads across multiple apps, so not just the browser app. However, 86% of ad blocking apps that are out there on the Google Play Store only block ads within the browser app itself. There is an AdBlock Plus version that blocks ads across multiple apps, but it requires either a rooted phone or a complex Wi-Fi proxy setup that is not suitable for the average user. In the literature side, there has been some recent work, for instance at NDSS of this year, that collected a lot of mobile data from many different users, and they looked at the communication graph between apps and domains, and if more than one app contacted the same domain, they labeled it as a potential tracker. And I'm simplifying things a little bit. But in the end, they have a list of domains, so again, this is not as fine-grained and can lead to some broken apps if we use this domain-based list. Slightly different direction here was Recon, where they looked at different packets and they used a classifier to predict whether or not a packet contains a piece of PII, and their solution ran on a VPN server where they applied these classifiers. So in our work, we tried to combine all of these good things, as I will show you in the next slide. So obviously, we want to block ads, so we train on some mobile data. We use a machine learning approach where we have a classifier sitting on the device, and given a packet, it predicts to us whether or not it contains an ad request. So that we can block ads across multiple apps, we again use a VPN-based approach that does not require a server. With that come a few efficiency challenges, but luckily there has been a lot of related work that has already been done. So we built on top of AntMonitor to gain that efficiency, and we do a few more tricks to make sure the classifier can also run in real time. So for the rest of this talk, I will go through each component of our system. It consists of roughly 4 components. We have the server that does the training of the classifiers offline. We have the AntMonitor library that runs on the device and intercepts the packets. We have the classifier that predicts based on the packets, as I showed you in the previous slide. And we have a data collection mechanism because we need some ground truth to train our classifiers. So I will start with the data collection. We started out by testing the top 50 most popular apps, and we started with EasyList as a labeler for our ads, and then we added rules to it to make them more mobile specific. So we interact with the app for 5 minutes. If there's no ads being shown, that means EasyList labeled all the packets correctly. We save the packet traces and their labels and move on to the next app. If we interact with the app and an ad is shown, that means EasyList is not complete, so we try to create a new rule, add it to our list, and then test the app again. From here, a few things can happen. It's possible that the same ad might be shown. That means our rule was wrong. We need to delete it and try again. We interact with the app again. Possible that a different ad might be shown because apps will keep trying to fetch an ad if the first thing is not working. So we need to create yet another rule. And we can get stuck in this loop for a while, but hopefully eventually there's no more ads and we can save the packet traces. To summarize our data set, we have 50 apps, about 15,000 packets, 4,500 of which contain ads. And with just these 50 apps, we were able to cover 41 ad libraries. So if I have a graph over here of our data set, on the x-axis we have the ad libraries, and on the y-axis the blue bars show the number of apps in our data set that contain that ad library. And the orange line is the percent of total installs on the Google Play Store that contain this ad library. So as you can see, the ad libraries have a long tail distribution. So to gain a comprehensive view of the ecosystem, we really need to worry about the top 30 or top 40 ad libraries. And in fact, our data set covers all libraries that account for at least 2% of all installs. This is the first mobile ads data set that we're aware of, and we made it available on our website as a contribution to the community. We hope that it will be useful to other researchers. Because if you use EasyList alone, it's not enough for the mobile ads data to collect a good mobile ads data set, as it fails to detect 37% of ad requests. So it can detect ads by popular ad libraries such as AdMob and MoPub, which have desktop counterparts, but fails to detect other popular ad libraries such as Unity Ads and AppsFlyer that are over there. And as you can see, they have actually a lot of installs, so they're quite important. So that concludes our data collection mechanism. Next, I will go through how we train our classifiers. So first, if you look at how popular lists perform on our data set, we see that EasyList has a 77% F1 score, and other mobile lists that are host-based perform even worse. So just to see how our classifiers can perform on a network layer features only, we trained some decision trees using destination IP and port number, and then also the domain. And with just these network layer features, we were able to already gain better performance than the lists, having about 87% F1 score. But then we wanted to see if we can do better by looking deeper into the packet. So for that, we looked to Recon, and we changed it to predict ad requests instead of PII, and made it run on the device instead of a VPN server. So if you look at the packet, it looks something like this. And from this packet, just by looking at it, we can already kind of tell that this is an ad request. It's going to ads.mopup.com, it has this /ad, and it's sending the width and heights of the device so that it can fetch a properly sized ad. So what we did is we break this packet into words based on various delimiters, such as the equal sign, ampersand, or question mark, and we end up with a vector of words. We repeat this procedure for all the packets in our data set, and then we end up with a huge list of words that are the features for our classifiers. So if you look at the decision tree that's trained on the URL, we already have a much better performance, about 93% F1 score. But because now we have this list of words, our number of features goes up to thousands, and now our training time is in orders of minutes instead of milliseconds, which is still fine because it's running offline. And our resultant tree size is still small, 196, which is orders of magnitude less than the lists that have like 64,000 rules. If we add headers to our decision tree, we do even better. And this makes sense because EasyList actually takes on the HTTP referrer header. So it makes sense that it helps in our classification. Because we have more words, again, our training time goes up a little bit because the number of features goes up. Next, we looked at if other contextual information can help us in the classification. For instance, whether or not a packet contains some PII or the application name. And these extra features do help in the classification. Actually, with the app name, we achieve the best performance. But in reality, we might not have the app name when we're trying to predict on an app that was not part of our training set. So the more realistic case is where we use the URL headers and PII classifier, so I will focus on it for the rest of the talk. If you look at our classifier, here's a sort of partial view of it. At the top of the tree, we have the most important feature. In our case, it turned out to be DNT, that do not track. And from there, the tree splits on other words that make intuitive sense, like ads.mopup.com makes sense if a packet contains that, it's labeled as an ad. If you look deeper into the tree, we still have more intuitive features as well. In this case, we have a piece of PII, advertiser ID. So these can actually be helpful to somebody trying to create a list. They can look at the tree for some suggestions on how to create rules. To summarize the training, the more information we use, the better our F1 score, and the classifier of choice, the URL headers and PI, performs quite well. Our code is also available on the website, so you can reproduce our results with our data and the code. The results I showed you earlier were based on cross-validation based on packets, but we also did splitting based on app names. So we split the training and test sets based on the apps. And even in that case, 70% of apps had an F1 score of over 80%. We also looked at how ad libraries fit into the performance and found that even in the cases where the ad library overlap is below 100% between the training and test sets, we can still achieve an F1 score of about 100%. So this concludes the training section. Next, I'll go into how we achieve the real-time machine learning on the device. So the main problem here is we want to avoid this parsing step. We really want to avoid Java, string matching, and regular expressions on the mobile device because we have limited CPU, and we want to run in real time. So for that, we looked into our tree for some intuition. We really need to worry about the words that appear in the tree, and again, our tree size is small. So if we just extract these 100 words, we can use very efficient deep packet inspection mechanisms, such as the native C implementation of the Acar algorithm that's already provided by Monitor, and it can find multiple words in one pass of the packet in less than 1 millisecond. So now, given a packet, we just look for these words. In this case, we find the DNT and the ads.mopup.com, and we pass just these two features to the classifier. The classifier then goes through, says, OK, DNT, ads.mopup, and spits out that this is an ad. So this is the first time that we know of that we were able to achieve on-device per-packet classification that can run in real time. We did some evaluation testing and found that we can extract the features and apply the classifier in about 3 milliseconds. And most of the delay comes from the application of the classifier, not the deep packet inspection. We did a few more improvements recently and got an even lower number, about 2 milliseconds per packet. So to conclude, I presented to you NoMoAds, which is a system for effective and efficient machine learning for ad blocking on the mobile device. And for future direction for NoMoAds, we are looking to increase our data set by maybe making the process more automated. Right now it's very manual. We're also looking to detect if we're breaking the app by blocking ads. And we are looking into extension to trackers, so not just ads. So thank you very much. And as a reminder, our code and data set is available on our website.
Hello, any questions? Okay, Jeremy?
Thanks, really interesting talk. I enjoyed it. I'm curious what percentage of false positives you're getting and what percentage of false positives do you think is acceptable to a user of a mobile device because it breaks things, or maybe I missed that.
That's a great question. So we actually looked more closely at the apps and the number of false positives that we're getting. I have a backup slide here somewhere. And the number of false positives is quite low. And then we looked at the packets that are generating these false positives, and they still have curious strings like ad format equals video or reward tracker. So these are probably actually OK to block. The app doesn't seem to break still. So maybe it means even our rule set is incomplete, and we should be blocking more. Does that answer?
Well, the second part is how much false positives will users tolerate?
So that's where we want to see if we can detect app breakage. So far, we have not seen that the apps break with our classifier. So as long as we're not breaking the app, and even though we're not generating false positives, I think the users can tolerate that.
Question back
here. Like you said in the introduction, one of the problems with the conventional way of blocking ads is to not break functionality. What about the apps that actually require an ad to play to continue? Is there a way to know this beforehand and actually maybe allow these apps to not break functionality?
That's a great question. So far, we haven't seen anything like that, but maybe in the future, as we increase our data set, we will. And in this case, we'll have to tell our classifiers to allow this ad. We can maybe use like static analysis approaches to examine the app code and then see if they're actually requiring the ad to be shown.
Any more questions? I have a quick question, which is, you've been mostly focused on blocking the ads, but you sort of get some tracking protection built in. Did you measure sort of how much of that is true?
How much tracking?
How much protection against tracking you get with this?
We did not measure that. We did not have the tracking list, but that's part of the future work to extend to trackers.
Cool. Ian.
Hey, thanks. When you block, so you get the packets one at a time. You're operating in VPN mode. So if you see a packet that has a GET request for an ad, do you just drop it? Do you reset that TCP connection? Do you send back a 404? Like, how do you
Excellent question. Yeah, if we just drop it, they will keep trying, right? TCP retransmission, and that will eat up the device. So we found if we just send an HTTP empty response, that seems to shut it up a little bit, and it works.
Okay.
So did you try if this works across different locations or places, or is all of your data set collected locally in the US? Because different places have different ads. Is something, like, what do you think about it?
That's a good point. As we're looking to extend our data set, we're going to try to use like an emulator mode, and then we can fix different locations for it. For now, yes, unfortunately, we've been all done in the US.
Thank you. The list of suspicious strings that you show there and you've shown elsewhere makes it sort of appear that the ads are not doing anything to obfuscate that they are ads. But if a system like this became popular, probably advertisers would react by starting to obfuscate their ads in order to not get blocked. Do you think a system like this has a good chance of surviving that arms race? Or do you think you'd need to proceed in a different direction entirely?
That's a great question. That's one of some of the reviewers' comments. So people that have been blocking PII, personally identifiable information leaking out of the device, have also looked if apps obfuscate the fact that they're leaking these strings. And so far, obfuscation has been quite minimal. So we're hoping the same will be with the ads. But even if they obfuscate, we can keep retraining the classifiers. This is the nice thing about having a machine learning approach.
Okay. Thank you.